Hello, welcome to this video lecture. In this video, let us discuss about simple harmonic motion. We see different kinds of motion every day. The motion of simple pendulum, motion of swinging weight in a pendulum clock, oscillation of mass spring system, etc. In all these examples, you observed object moves to and fro along the same line, and motion keep repeating themselves. Such motions are periodic in nature. This type of motion is known as simple harmonic motion, in short SHM. The points to be remembered when we consider simple harmonic motion. A particle or body moves to and fro motion about a mean position under the influence of a restoring force. The direction of motion is directed towards the mean position. The magnitude of restoring force is proportional to the displacement, such that F is proportional to minus x. Characteristics of simple harmonic motion. The system must have inertia. Restoring force is proportional to the displacement. Body must have acceleration in a direction opposite to the displacement. Simple harmonic motion is an example for periodic motion. It can be represented by a simple sine or cosine function such that x equal to a cos omega t plus or minus phi. Now let us derive an expression for simple harmonic motion. For this, consider a spring with spring constant K and mass m is attached to it. As a result of this, springs start oscillating from its mean position. A restoring force is developed within the spring, which opposes the oscillation of a spring. The expression for this restoring force may be given as F is equal to minus Kx, where x is the displacement and the negative sign indicates the restoring force is always in a direction opposite to the oscillation of a spring. The force which makes the system to oscillate is given by Newton's second law, F is equal to m into a, where a is acceleration, which is nothing but d square x by dt square. At equilibrium, both the forces which make the springs to oscillate and the force which make the spring to stop from its oscillation are equal. Therefore, we can write minus kx is equal to m into d square x by dt square. Therefore, we can write d square x by dt square plus k by m into x equal to 0. In this expression, k by m is nothing but omega square, where omega is equal to square root of k by m, which is nothing but the natural frequency of a system. Therefore, we will get d square x by dt square plus omega square x equal to 0. So, in this expression, if we consider d by dt is equal to capital letter D, then expression 4 becomes d square x plus omega square x is equal to 0. So, I will take it out the common term in this expression, that is x. So, I will get the expression as d square plus omega square into x is 0. Here x is the displacement which never be 0. So, the only possibility is d square plus omega square is equal to 0. This implies d is plus or minus I omega. So, these are example for second order differential equation. The solution of this expression may be in the form x equal to y cos omega t plus z sin omega t. Here y and z are constants. We need to determine the value of y and z by applying boundary condition. The first boundary condition says that when t is equal to 0, the displacement is maximum. Therefore, we can write x equal to a. When we substitute this boundary condition in expression number 5, we will get A is equal to y cos 0 plus z sin 0. Cos 0 is 1 and sin 0 is 0. Therefore, we will get y is equal to A. To determine the value of z, we need to apply the second boundary condition. That is, when t is equal to 0, dx by dt is 0. So if you differentiate expression 5 with respect to t, we will get dx by dt, which is equal to minus omega y sin omega t plus omega z cos omega t. Since t is 0, we will get dx by dt is equal to minus omega y sin 0 plus omega z cos 0. Dx by dt is 0, sin 0 is 0 and cos 0 is 1. Therefore, we will get 0 is equal to omega into z. Omega is angular frequency which never be 0. Therefore, only the possibility is z equal to 0. Now, if we substitute the value of y and z in expression number 5, we will get the solution for simple harmonic motion. Therefore, the solution for simple harmonic motion is given as x equal to a cos omega t. In general, it may be written as x equal to a cos omega t plus or minus phi, where phi is the phase. Thank you for watching this video.